As you can see from the title of this video, this tutorial is about learning how to write the formulas or names of ternary ionic compounds. Previously we talked about how to identify binary ionic compounds, and we learned that there was a system for writing formulas that has us write symbols and charges, cross those charges, and reduce. You're going to find ternary ionic compounds are fairly similar because, again, they're still ionic. Ternary prefix simply means to us that now we have more than just two elements. So if we're going to look at identifying and writing these, the main characteristics of ternary ionic compounds is that they are made up of more than two elements. And we can get even more specific than that. We'll learn that ternary ionic compounds are formed between one of two things. You will either see a metal plus a polyatomic ion, or the polyion, specifically ammonium, plus a nonmetal. So the two ways ternary ionic compounds tend to form are we have a metal from the periodic table with one of our negatively charged polyions like sulfate or carbonate, or you'll have ammonium, one of the positively charged polyions, with a nonmetal from the table like sulfur or oxygen or chlorine or fluorine. From here, you'll notice that the ternary ionic are very, very similar to the binary ionic. So when we did binary ionic, we learned how to write the formulas first and then write the names. So we'll try to follow that pattern. We're going to list a series of steps that teach us how to write the formula. We'll do some examples, and then we'll go back and learn how to name them. So if I want to write the formula for a ternary ionic compound, the first thing I will do, right, just like before, is write symbols with charges. The only difference this time is that one of your symbols is going to be a polyatomic ion, something that has more than one thing in it. Right? So write symbols with charges, and then I'll add just a little bit here that sometimes it helps to put the polyion in parentheses. Step 2, just like with the binary ionic, we're going to cross the charges, again, in number only. Right? We're only going to cross the charges in the number only. Right? Another reminder here is going to be that you cross the charges outside the parentheses. Step 3 is to reduce if possible. Right? So we'll reduce if possible. And a big reminder here is never touch the formula of the polyion. Right, so you'll learn the idea is something that can come and go. We'll do it early on so that you get the hang of not doing anything with the polyion other than crossing its charge down. But the big thing I always want you to remember is you can never change the subscripts on a polyion. For instance, you will never want to reduce SO4 to say SO2 because SO4 is sulfate. If we change SO4 to something else, it is no longer sulfate. So you have to realize that whenever you are trying to reduce, you only reduce things that get crossed down outside of the parentheses. So let's take a look at a couple examples. The first example we want to look at is something like calcium phosphate. Calcium phosphate, right, we look at that and we have to decide, how do I know there is a polyion in here? Right, and the trick to knowing it when you're looking at the words is by zeroing in on the ending. Like, two key endings that always tell us polyions are ate and ite. Now I'm going to go in and I'm going to add that here as one of our characteristics. Right, more than two elements, it's a metal plus a polyion, or ammonium plus a nonmetal. Right? But the biggest thing that will indicate it is you will see an ATE or ITE ending. Once you realize that you've got a polyion there, right, then you can just proceed into our writing the formula steps. There are three exceptions to that rule. There's three polyions on our list that don't end in IDE, so you just have to be careful that you keep your eyes open for them. Those three polyions are hydroxide, cyanide, and peroxide. They're the only three polyions that we will work with that do not end in ate or ite. So, if we push on into writing the formula for this, the first thing we'll do is write our symbols with charges for what we have up here. So calcium symbol is Ca. Because it's in group 2, calcium gets a +2 charge. Phosphate, you're just going to have to know. The polyion phosphate is PO4, and phosphate carries a charge of -3. Right? This is why we will take quizzes on your polyions, because there is no way you can look at the word phosphate and do this if you don't know what phosphate is. The periodic table can help you with calcium. There's nothing that can help you with knowing phosphate's charge other than memorizing it. Step 2 says cross the charges outside of the parentheses. So just like with binary, I'll bring the 2 down to here and the 3 down to here, all outside the parentheses. So if I do that, I will get Ca3 PO4 2. The 2 went to here, the 3 went to here. Third step is to reduce if possible. And here's where you have to be careful. What we are checking to see if it reduces is what we cross down. I'm seeing if 3 and 2 can reduce. And the answer is no. That's as simplified as it can get. Right? You cannot think, oh, I'm going to reduce the 2 and the 4 here, or the 1 and the 3 here. That is why I mentioned never touch the formula of the polyion. You can never reduce PO4 to anything because it would no longer be phosphate. So 2 and 3 is what we're checking, and I'll underline it just so you can see. Right? And you'll find that we cannot reduce the 3 and the 2. So the formula for calcium phosphate will be Ca3 parentheses PO4 parentheses 2. Taking a look at a second example. How about we look at something like gold II sulfite. Gold II sulfite. Again, as I look at this, I have to decide. Is it ionic? Is it covalent? How can we tell? Well, if you take a look, gold lies to the left of the staircase, so it's a metal. Sulfite has an ITE ending, and an ITE ending is a big indicator of a polyion. And so that means we're going to have to follow our rules for ternary ionic. And so that first step tells us we should write symbols and charges. So the symbol for gold is AU. And AU's charge, if we look to the periodic table, is in one of the groups we don't know by telling the table. Right? And it's not one of our three from the transition metal that we're supposed to know, A, G, C, D, or ZN. So there better be a Roman numeral that tells us the charge, and sure enough, there is. So the charge on gold is going to be +2, because the Roman numeral II is what 2 is. Then you have to know what your polyion sulfite is. The polyion sulfite is SO3, and it carries a charge of -2. So we list our symbols and charges, and step 2 says cross those charges. So we're going to cross the charges down, again, only in number, and when we do that, we get AU2 parentheses SO3 parentheses 2. Step 3 says reduce if possible. Right? So what we are checking is, does 2 and 2 reduce? And the answer to that question is yes. They're both divisible by 2, which would lead us to a formula of AU SO3, and it would be 1 and 1, and we never write subscripts of 1, and if we only have 1, we do not list the parentheses. So the correct formula for this would be AU SO3, if I were going to name correctly gold 2 sulfite. Let's try 2 more. What if we took a look at something like magnesium chlorate? Again, we look at the name and we decide, is it ionic or covalent? Well, magnesium is to the left of the staircase, which makes it a metal. Chlorate ends in ATE, right? And because it ends in ATE, that means there's a polyion. So anytime we realize it's ionic, all we do is symbols and charges and cross them down. Right? So magnesium, as we said, is Mg, and it gets a charge of +2, because it's from group 2 on the periodic table. Chlorate is a polyion that you will have to know. Chlorate is ClO3 -1. So step 1, you list your symbols with your charges. Step 2, you cross your charges. The 2 going here, the 1 going here, which would lead us to Mg parentheses ClO3 parentheses 2. And the question becomes, do 1 and 2 reduce with each other? And the answer is no. That's as simple as it can get. So magnesium chlorate's formula will be Mg parentheses ClO3 parentheses 2. Right, last example, show you one that's a little bit different. Let's try ammonium carbonate. So as you look at this one, right, we want to identify, is it ionic, is it covalent? Right? You see ammonium, and ammonium is nowhere on the periodic table, so right away you know this is an ionic compound. Right? Different in 2 ways. Because we have ammonium, we could have a non-metal here from the table, or we could run into an instance where, because this ends in ATE, I actually have 2 polyions. And that's perfectly fine to have two polyions together. One of them just has to be positive. The good news is the rules that we'll use remain the same. I write the symbols with the charges and I put the polyions in parentheses. So ammonium is NH4 plus 1. Carbonate is CO3 negative 2. Right? So you'd have to look up those on your polyion sheet for now, but later on you'll know them. And now the only difference is we just have two things in parentheses for when we cross down. The 1 will cross to here, the 2 will cross to here, and what you end up with is NH4 parentheses 2 CO3 parentheses 1. We check to see if 2 and 1 can reduce. They cannot. So this is good the way it is. The only thing is we don't leave 1's in parentheses if it's a 1. So we just simply drop the parentheses and get that the correct formula for ammonium carbonate is NH42CO3. So notice, very, very similar to what we did with binary ionic compounds. The only difference is you get a polyion that has a charge to cross down instead of just a separate element that crosses down. So there's the one half of the street. How do we write the formula if we're looking at the name? What do we do if we are looking at the formula and we want to write the name? So let's take a look at that. So in your notes, call this writing the name. And if we're going to look at the steps to writing the name for ternary ionic, usually what I do is I see that I have 3 or more elements, because that's the way you'll know it's ternary ionic. And the first thing I do is I put the polyion in parentheses, or underline it, or box it, some way of identifying in a formula which part of it's the polyion. Now, in some of them it's very easy, it's done for you. Right? If I give you Ca3PO42, I have to put the parentheses there. But in something like this, AuSO3, I would have to identify the polyion. Another way you can tell is the polyion part is always going to be the non-metal part. Right? So if you look at a compound that has 3 elements, find the 2 of them that are non-metals, and that has to be the polyion. Right? Until you get them memorized and they'll just stand out, that will help you. Right? Step 2 is we name the metal. Or we'll say, let's name each part of the compound. Right? So you name the non-parenthesis part and then the parenthesis part. Right? One of them is going to be just like off the periodic table, which is usually the metal, and then the other is going to be identical to what you see on your polyion sheet. Last but not least, just like with binary ionics, you have to check if transition metal and if it is a transition metal, determine Roman numeral. And remember, there are a few exceptions to that rule. 3 transition metals that we never give Roman numerals to are silver, cadmium, and zinc. Right? Silver, cadmium, and zinc are exceptions. let's take a look at a few examples of how we write the names if we are given the formulas of some different ternary ionic compounds. First example, Ca parentheses BrO3 parentheses 2. So, as I look at that compound, the first thing that I need to do is figure out, is it ionic or covalent? Right? Because I see 1, 2, 3 different elements, right away I know it's ionic. Because the only types of compounds that we will have that have more than 2 elements are ionic ones. Then, once I identify this as ionic, I want to follow my steps to getting the name. It says put the polyion in parentheses. Well, because there's more than one, that is already done for you. Step 2 says name each part of the compound. And so the first thing I'll do is I'll name the first part, and Ca is the symbol for calcium. Naming the second part of the compound, BrO3, the polyion, is called bromine. So calcium bromine. Step 3, check if the metal you wrote was a transition metal, and if it is, determine the Roman numeral. So you take a look at your periodic table. Our metal was calcium. It's in group 2. Group 2 is not a transition metal. Remember, it's the middle section, the DE block, groups 3 to 12. So because calcium is not a transition metal, we're done. Calcium bromate is correctly named. What if we look at something like AgClO4? Again, if you look at a formula, first thing we need to figure out, is it ionic or covalent? So taking a look, I see that I have Ag, which is a metal, right? Cl and O, 3 elements, tells me right away it's ionic, right? But I'd have a metal and a non-metal and a non-metal, which also tells me ionic. So I put the polyion in parentheses. Right? Here's a good case that parentheses weren't given to us. So if you don't recognize who the polyion is right away, how you can figure it out is by looking here. The polyion is the non-metal portion. So Ag is your metal because it lies to the left of the staircase. Cl and O are your non-metals. That means that this right here, the ClO4, is the polyion part. Step 2 says, name each part of the compound. Well, the first part is Ag, and Ag is the symbol for silver. Naming the second part of the compound, ClO4 is the polyatomic ion perchlorate. And then lastly, step 3 says, check if it's a transition metal, and if it is, determine the Roman numeral. So we find silver. Silver is in group 11, which is a transition metal. And then once we figure out it's a transition metal, we check, is it one of our exceptions? And sure enough, silver is one of our exceptions. So what that means is we think it should get a Roman numeral, but because it's an exception, it does not. So AgClO4 is correctly named as silver perchlorate. Taking a look at another one, how about Fe3BO3 parentheses 2? Okay, taking a look at this one, I first decide ionic or covalent. Because I see 3 elements or more, I know it's ionic. Put the polyion in parentheses. This time again, it's already done for us because I have more than one. Then, name each part of the compound. Fe is the element iron. BO3 is the polyatomic ion borate. B-O-R-A-T-E. So I named each part, the Fe part and the BO3 part. And then now I check, is iron a transition metal? So we slide our periodic table over. Fe is in group 8, so it is a transition metal. Is it one of our exceptions, silver, cadmium, zinc? It is not. So that means we have to figure out the Roman numeral form. Remember, when we're trying to get the Roman numerals, the first thing I try to do is uncross the charges. Right? If I uncross the charges and the correct charge ends up on borate, whatever was here will be correct for iron. If that doesn't work, then we create the table. So let's look. If I uncross, I put a 3 on borate and a 2 on Fe, right? The 2 would uncross to here, the 3 would uncross to here. Is 3 the correct charge for borate, BO3? You bet it is. Which means the 2 that goes up to iron will also be correct. So this is iron, II, borate. Let's take a look at one more. Right, last one we want to look at, I'll put right over here. Let's take a look at NH4Cl. So if we look at NH4Cl, and I want to write the name for it, first thing I'll see is that NH4Cl has 1, 2, 3 elements. That tells me there's a polyion in there. So we put the polyion in parentheses according to our rules. Right? So if we take a look, our polyion is either going to be NH4 or H4Cl, and hopefully we'll recognize that NH4 is our polyion, right? The nonmetal plus hydrogen. Then we'll follow our steps. Put the polyion in parentheses, which we have. Name each part of the compound. NH4 is called ammonium. Right? And a little adaptation that you have to make, right, whenever you have ammonium is we have chlorine second. Right? But we never let nonmetals end in INE. We never name things something chlorine. Right? You'll remember from the binary, nonmetals always end in IDE. So if something's with ammonium, it's going to have an IDE ending. Ammonium chloride. Right? The only time it won't is if it's with another polyion, which would be like an 8 or an 8. Right? So remember, the second part, if it's not a polyion, always ends in IDE. Last but not least, we'd have to say, is ammonium a transition metal? The answer is no, it's a polyion. So ammonium chloride would be the correct name for NH4Cl. Right, so that's a little lesson there on ternary ionic compounds and how you name them. Notice, very similar to binary ionic compounds. Right? When you're looking to write the formula, symbols and charges, cross and reduce. And if you're looking to write the name the metal, name the polyion, or if there happens to be ammonium, the nonmetal with an IDE. Hope this helps out in what we're trying to do.